Hello there. Today we'll be doing list partitioning. Given a list of strings containing the strings red, green, and blue, partition the list so that the red comes before the green, which comes before the blue. This can be done in O of n time, and the bonus is if you can do it in O of 1 space. That is, can you do it by only rearranging the list without creating a new list of strings? So an example of what this means is that we take these strings, green, blue, red, and red. We move the reds into the first spot, take the greens, put in the middle spot, and take the blues and put at the end. There are several solutions here. The first solution that we can think of is sorting. We could use the sort algorithm, and that would give us an n log n time. We could sort this two ways. We can use a lambda function to sort it in any color formation that we want, or we can sort it in reverse because it is red, green, blue, which is a follow that structure. This is very easy for me to show immediately, and so I'm gonna do this right now, and we're gonna move on to a O of n approach, with O of n space in two loops, and O of n two loops in O of 1 space. And then we're going to finally get to the most efficient solution as the scalable solution as the number of items increase, which will take one loop and O of 1 space. But I mean, who doesn't want to see if the product's working, or at a a smaller scale first? And you can do this in such a short amount of time. So let's do it. So first thing you're gonna do is strings.sort key equals lambda of x. In this, we're going to create a red, a green, a blue, and dot index of x, and we're going to return the strings. So this is going to sort these items in this particular order. Run and submit. Perfect. So a way we can speed this up and not apply a random a function that is not quite optimized is to use the reverse function. So by doing the reverse function, of course this does not apply to all the cases of colors. Suppose we have a different color that does not run in like orange or something, right? And it's suppose orange goes first. So let's run and submit. Okay, pretty fast. Now, of course, this is not the optimal solution, and we want to optimize. So maybe we're going to delete this now, and we're going to do two loops. So first thing we're going to do in this solution is go through all the items, count all the items, number of red, number of greens, number of blues. Then we're going to put those numbers into the correct spot and return our string. So we're gonna do this with numbers because I don't want to go through the complexity of dealing with a data structure like a dictionary. But if I think as our number of colors grow, I think a dictionary makes a little bit more sense because it's a lot more maintainable. So why don't we just go with a dictionary instead then? Let's go with a dictionary then. Okay. So originally we're gonna do num red, num green, and num blue. And then we're gonna just add up all the greens, blues, and reds, and then create a list, return like red times num red and plus you know, num greens. Oh, my fingers are not working. And plus num blues. Of course, we have to do this in place, but we just have to count all the num reds and num blues and num greens. But instead of this, let's just use dictionary, because it's just more scalable, right? So this is 0, green, 0, and blue. You can imagine like this code being like this, like, you know, and we can always use enums to make this more, you know, functionable. Anyways, so frequency for strings, for s in strings, frequency of the s plus equals 1, and instead of, we're just going to get the frequency of red, green, and blue, and we're going to return and submit. All right, pretty quick. Of course, this is not going to be as quick as having individual numbers, because we don't have to access a dictionary and go into memory and get that information. We have it, you know, very quickly. So why don't we show that? Let me show that way of doing it, and then we can go into the O of 1 space solution afterwards. After I show you, this is cleaner for people to see, but it's a little bit slower for code. So let's reverse, go back. All right, let's get this. So for I in range of lang strings, we're going to count all the items in the strings. So if, well, actually, we can just do s and string. This is a lot faster. If s equals red, num red plus equals 1. Else if s equals green, num green plus equals 1. Else, well, num blue plus equals 1. Of course, we can change this later, but let's keep this on for now. And run. Oh, the little typo here. Submit. Wow, extremely fast. See? So let's get this O of 1 space and put this together. Okay, so O of 1 space, we just have to go through another loop for I in range, length of strings. So we're going to go through every item in the strings. Set strings of I equal, so if num red is greater than, let's say, 0, so there's items in there, num red minus equals 1, and this we're going to set to red. Once we run out of number of reds, we're gonna set the greens. So num green minus equals 1. Strings of I is equal to green, and else, you know, the last of this is going to be equal to blue. We don't have to do any subtraction yet, because we just don't. I mean, not yet, but we're going to have to deal with it later. So there, we have another solution. As you can see, because we sacrificed space for time, yeah, so that's exactly what happens. Okay, All right, now on to the single loop, because this way this is the most scalable solution because we're going to go through all the items once, and we use O of one space. So this solution requires us to swap the positions. This is like the Dutch flag problem. So let me explain. So this needs a little bit more visualization because it's less about, because we're going to be swapping things, and this is important. So here's the start, and here's their index. So whenever we see a red, we're going to replace it with this particular item. So red and green swaps places. Then we're going to move the start and move the index to the next item. We see blue. Sorry, that's not how it works. So we have index. Is this one loop? No, this is 3 loops. Okay. Actually, okay. Well, we move the I here, and we swap. We're trying to find all the reds and swap them with the items here. And so we keep moving the I, and every time we do a swap, S moves forward. So I is going to be red. So red swaps with blue. So as you can see here, we have the red, green, blue. But this is not the end yet, because we have to move the S after a swap. And we need to move the index back to green. And green swaps with green, so we're going to move the S. And this is going to be stay green, and this is blue, and everything else remains blue after all the swaps. So you can swap as many colors as you want, but it looks like to me that it is possible that we this is technically 1.5 loops, because like, what if we go all the way to the end and get all the reds, and afterwards we don't have to deal with the reds anymore, and then we start at that particular point and it's halfway or whatever it is, or you know, maybe it's even 1 spot forward and we find 1 red at the end and we swap that 1 red, and there's also a green at the end that we have to swap once. I mean, a blue at the end that we have to swap once with a green, right? And or a green at the end swapping with a blue in the beginning. So that, I mean, that might be 3 loops. 2 loops. Well, technically, this is for most cases, this is the most fastest solution at scale. So let's do it. This is called partitioning, and we need the strings. We need start points, and we need the word. So for the beginning, I in range of start, and the length of S. If S of I is right, make this shorter for us. So f of I is equal to the word, and we're going to start swapping that particular word with the start word. And then we're going to move the start forward. So now let's set the start position to partition starts 0 and red. Then we're gonna do the partition. Of course, we don't need to store the start anymore because we don't need to continue sorting. And we're gonna return strings. Run. Uh-oh. All right, and perfect. And that, I think, is the most scalable solution available in list partitioning at this point. If you know anything that is better, please let me know. I'll be happy to learn and see some more new solutions. And If you enjoyed the video, please like and subscribe. And if you want more, there is a link in the description below with more algos and what I'm be doing in iOS. And that's all. Thank you very much and have a good one.